Now we turn to the subject of effective stresses. And to be honest, this is a subject that is extremely important. It actually builds upon a great deal of the stuff that we've talked about already. It also builds on some knowledge of fluid mechanics, but it seems to be one of the most difficult things that students have to understand. And yet a great deal of soil mechanics in terms of the strength of the soil is based upon being able to do effective stresses properly. So we're going to try to do the best we can to lay this out in a step-by-step basis. Stresses in soils. Soils, there are, to analyze the effective stresses and beyond that, the effective strains in materials is a core of engineering. Whether it's civil engineering or particularly with civil and mechanical engineering, that is definitely at front and center. And particularly with solid mechanics. And even a soil material that is kind of dicey in a lot of ways in terms of whether it's a solid or a fluid, because sometimes it shows the characteristics of one and sometimes the other and sometimes of both. Nevertheless, the thing about the soil, first of all, and the first thing we need to understand is that we're not, traditionally we start with the assumption, and with most engineering materials, that they're in an unstressed state and then work from that. In soils, we can't do that because soils, by their own weight and by the effect of gravity, are stressed when we start, and then we come in there and add stress to it. And occasionally we'll take away, but usually we add stress to it, and the understanding of what's there to start with is essential. And there are several types of stresses, and I list them here. We have total stress, and then we have pore water pressure, and effective stress, which is the difference between is the first minus the second. So we'll see upward and downward seepage stresses when fluids move, and then there are lateral earth pressures. There's also external loads. We've got elastic methods and empirical methods. And we're going to talk about those a little bit later on. And then we take all that and throw it all together and find out whether it will induce failure or not. And sometimes we have to define failure as well. With Moore circle and theory of elasticity and plasticity. And ultimately, we'll also talk about the effect of particle rearrangement and consolidation. The principal source of soil stress is by its own weight. And those additional stresses can and will be added, as I mentioned earlier. So let's see if we can take this one step at a time and go through it. Let's start with hydrostatic stresses. And those of you who have me in fluid mechanics laboratory remember me talking about this. And by the way, for those of you who have either not had me in fluid mechanics lab or are outside of UTC and are looking at this, I've got all those lectures online too. All those lectures and all those experiments are online. Okay. The stress and under hydrostatic conditions, the stress is induced by the weight of the water at a given depth, or is equal to the unit weight of the water times the depth from the surface. At the surface of, this is kind of the scuba diver's equation, where at the surface of the water we assume that it's atmospheric. These are all gauge pressures. We don't fool around with absolute pressures in soil mechanics. They're all gauge pressures. At the surface of the water, it's atmospheric. Essentially, gauge pressure is 0. As it increases, as you go down the, as you go further into the water, the pressure increases, and it increases because of the weight of the water on top of you. From the surface down to some point Z below the surface, and that's equal to simply the unit weight of the water, which varies a little with water, but not much. The biggest variation with water is whether it's salt water or fresh water, but that's a different subject altogether. And that as you go deeper, the pressure on you gets greater. And some of you are sitting there thinking that's the way it is with this course. The deeper we get, the greater the pressure. Well, the hydrostatics, and so therefore, as you get to the point where you either need to have to come to stop going deeper and come to the surface because your equipment and your body cannot handle it, or you need to change the way that you are going deeper in terms of the equipment you have. And so that is now the assumption behind that is that the water is at rest. It's not moving. So civils, let's breathe a sigh of relief and say that the only forces experienced is gravity. We're going to get into moving soils. Just don't get too comfortable. We're going to get into moving soils in a little bit, but for now, we're going to start with strictly motionless, static water. As I mentioned the last time, you remember we had soil was a conglomeration of solid particles and voids. And let's just assume for the minute, and it's a valid assumption for in this, that all the voids are filled with water. This is where, we think in free water, it makes sense that the deeper we go, the higher the stress. But that's also true in water which lives in the pores. If it's saturated, if it's fully saturated, from the point of full saturation downward, the upward part we'll get to, if it's saturated from its water surface, from the phreatic surface, the water table level downward, is that definition saturated, then the water pressure will increase in the same way. All other things being equal, nothing else going on, as long as it's just sitting there, it will increase in like fashion. Now, pore water pressure doesn't have to be hydrostatic, but we're going to assume for our purposes right now that it is. Okay, continuing onward. Let's leave water aside for a minute, and let's go to the concept of total stress. Total stress is the stress produced at any point by the overburden pressure of the soil. Now, what does that mean? Overburden pressure of the soil is exactly the same thing as the overburden pressure on the water on the scuba diver. In other words, we said that if for example, if water is 62.4 pounds per cubic foot, and you're 10 feet below the water surface, it's 600, you multiply 10, 64.2 PSF. The overburden, in other words, whatever is above you in the soil. And also the total stress will include whatever you put on top of the soil. And doing all that results in a total stress. Now we're just talking about the unit, and this adds up just like it does with water. In other words, unit weight times distance. Now, the tricky part with soils is that they don't all have the same unit weight as we saw the last time. That means we have to layer them. But in any event, and that's why this equation is in that form, because every layer may have a different unit weight. It definitely will probably have a different thickness, or an H. And so you just, what's ever stacked above where you're at is the total stress. I say it ignores the effect of pore water pressure. It does not ignore the effect of pore water weight. Pore water weight definitely enters into it, because as we saw the last time, pore water weight is a part of the soil weight. but it doesn't. We're not talking about pore water pressure just yet. It implies in general to either dry or unsaturated soils. It also applies to soils that are not that are saturated and anything in between. Now let's talk about pore water pressure. As I said before, the pore water pressure should increase with the depth under normal conditions. But we need to define what pore water pressure is. Pore water pressure is the pressure of the water within the pores or voids of the soil. It can be caused by hydrostatic pressure, and that's pretty much what we're going to stick with just for the moment. The rest of them, capillary action, seepage, and other things, we'll deal with most of those later. Capillary action, we're going to deal with this very soon. Seepage is going to take a little longer. We'll get to permeability. Now, first of all, the pore water pressure and the total stress are not the same. As I said, total stress is related to pore water weight, not pore water pressure, and that's true. And the pore water pressure can and usually is different from any of the stresses the soil experiences, but it has an effect on those stresses because the soil particles are fully immersed into the soil, and as a result, the water surrounds those particles and has a buoyant effect upward. You remember, again, I refer back to my fluid mechanics laboratory where we did a little experiment with the boat, and we had a situation where the boat floated because its weight was equal to its displacement. Well, guess what? That also applies to stuff which is completely underwater. And it's kind of, kind of interesting because, it doesn't matter. A submarine is the same way. The difference between a ship at the surface and the submarine is the fact that the submarine basically only has enough upward force by manipulating its ballast tanks to keep it from going up or down in the water. In other words, it's balanced. Whereas the ship at the surface wants to make sure that the displacement doesn't allow the water to get over the gunnels and send the thing to the bottom, like the Titanic did. So, either way, the water has a buoyant effect on the soils under the water table. And that includes all soils under the water table. The buoyant effect of the water, just like it was on the ship, is equal to the weight of the water the soil displaces. And what that does, it reduces it's an upward force on the soil particles that basically reduces what we call the intergranular pressure. Now, what in the world is intergranular pressure? As I mentioned before, maybe I'll go to the next slide, maybe I have a little bit. You notice that we've done the usual infamous thing we do in soil mechanics, is we've assumed in this little diagram right here that all of these are spheres. Whether they're spheres or not, soil particles touch each other, and they put pressure on each other. And if you've got, and that pressure is related to the force downward by gravity, the z times the z times the whatever weight or weights that are above it, that pushes the granules together. The buoyant forces in saturated soils pulls them apart and reduce those intergranular stresses. And that's why the alternative name for effective stresses, and maybe the more informative, is intergranular stresses, although you don't see that. Most geotechs don't use that term. Now, here we have theory. Now, I mentioned about the displacement. Again, if we had one in a vat of water, if we had one or empty, this is empty before we put water in. If we put more water in, we have the weight of this sphere and it bears down. If, however, we were to fill with water under it, the volume of water that displaces would put an upward force on that weight. And that it would reduce, among other things, that reduces most importantly the contact stress between the sphere and the bottom of the tank. Well, in soils it reduces the stress between the soil particles to each other, since there's no real, usually, bottom of the tank. Well, so now what does that mean for us? Do we have to go and compute every sphere? No. Although, one of the advances we're seeing in computational geotechnics is the use of models which model every particle, or at least lots of particles in the soil. And so usually most of what we're going to do in this course is going to be strictly aggregate. In other words, we take a lot of soil particles and we treat them as a unit. But that is coming. You're going to start seeing more models. And I actually gave serious consideration to doing that for my PhD thesis, and my math teacher, who is now our vice provost, Matt Matthews, talked me out of it. And I was thankful for that later, because sometimes the models are not quite up to where they should be, but in terms of stability and whatnot. So I'm glad we didn't go that route. But in any event, that's coming. And I think if we ever get those, it's going to really change the way that we look at geotech. But in the meanwhile, let's look in the aggregate, because most practical problems can be solved this way. If I do go through a lot of math, and I show the math here, and I'll let, if you're interested in it, you can look at it. But basically, what I can show is that in the end, that we're going to define the effective or intergranular stress of the particles is equal to the total stress, which we defined just before, minus whatever pore water pressure is between the particles. Now, pore water pressure, we're going to start with hydrostatic. It doesn't have to be hydrostatic, but for our purposes right now, and for most geotech purposes, they are. That definition is key to understanding the definition of effective stress, and drives our whole calculational scheme. Now, one other thing I want to mention is something, and sometimes I regret actually bringing this up, but I do it because this is the way it's done in reality. In reality, the way it's done is that a lot of times geotechs will take a shortcut. And this is particularly a disease of those of us involved in retaining walls. What we'll do is we'll do some more calculations and whatnot, and we'll come up with a definition of something called submerged unit weight. And submerged unit weight is simply the saturated unit weight. And soils do not exhibit traditional, standard intergranular unless they're saturated. Non-saturated don't, because you've got air in the voids. Is equal to the saturated unit weight minus unit weight of the water. You can also compute effective stresses by, instead of using total stresses minus pore water pressure, you can simply make them all saturated unit weights and compute, just the old compute like you do total stresses. That assumes the existence of hydrostatic conditions where the water is going nowhere. And that's only good in hydrostatic conditions. But that's an alternative, and the reason why I present it, again, is because that's the way geotechs do it, And you need to be aware of that and familiar with it. But leaving that aside for a minute, the total stress minus the pore water pressure is the classic definition, and for your problems, you should use this definition as your principle. In other words, I would avoid using submerged unit weights unless you're just forced to for some reason. This is the classic way. It's the best way to do it. It only considers the load of the soil itself. We're not getting into all this other stuff that you might put on top of it. You as a civil engineer, particularly on undeveloped sites, you're going to show up at a place which hasn't had anything on top of it for a long time, most of the time, unless it's a glacial till or something like that. And it's minding its own business, and you're going to go there and put something on top of it, and it's going to produce extra stress. So that's before that. It is one of the most important concepts in soil mechanics. Generally speaking, soil stresses increase as you go further down because of increasing height and weight on top of it. Varying the unit weight will vary the increase in the effective stress, obviously. Above the pore water pressure, water table, pore water pressure is generally not considered except for capillary conditions. Now, I'm going to be honest with you, we're not going to consider a lot of the ins and outs of unsaturated or partially saturated soil. Or unsaturated soils means the soil is not 100% water, the void is not 100% water. That gets complicated, but we're going to leave that aside. There are two methods to compute them, and I mentioned that my preferred method is this one. I've kind of gone over this already. I have a bad habit when I'm lecturing of getting ahead of myself on my slides, and I've done it. So this is the way you normally should do it. The way you do it is tabulate heights and layers of units, note the location of the water table, and use this to compute effective stresses. The submerged unit weight is basically the same, except that you change the unit weights rather than to subtract the pore water pressure. Again, this is your preferred method. I would leave this one out until you get a little more experience. To put all this together, we'd have to do something called a P-naught diagram. And the P-naught diagram is based upon the name that the FHWA has given it, and that's what we're going to call it. It's useful to visualize effective stresses, total stresses, pore water pressures, everything. And it can be used, and we'll show you how that's done, to, when we include other loads that we put on top of it, we're going to show how that works. And it'll be a little bit later, because first of all, I got to show you how other loads work when they get under the soil. These are important. These are very important, because they give you a way of visualizing what's going on in the soil. There are two ways of plotting them. You can manually plot them, and I've seen a lot of manual plotting. And that leads to another one thing that I've discovered is that drawing is, let's just say engineers don't hand draw the way they used to. The advent of computer graphics pretty much has laid that aside. And we just don't do it the way we used to do it in the past. You can manually plot them. A better way to do it, but it takes a little bit of setup to get going, is spreadsheet plotting, where you divide the soils out, and then you plot them. It's a little tricky because spreadsheets like to have the independent variable on the x-axis, then on the y-axis, and then go up like this. Whereas traditionally with effective stress, we put the depth this way, which is independent, and the dependent, which is the stress, and we go down like this. If you master that, then you can do it using a spreadsheet. And that can be a very useful way of plotting P-naught applying a P-naught diagram. Let's start with an example, and that example is in your Soils and Foundations manual book, and I've just reproduced it from there. That's one of the joys of using public domain stuff. You just throw it up there. You just copy it and throw it up on the screen, and you can keep everything together without you being inflicted with my handwriting. Some of my fluid mechanics lectures demonstrate that, and I'm sure that, just be thankful. But in any event, this is a 20 fine P-naught at 20 feet below the ground on the sand deposit. The total unit weight is 110 PCF. One thing you will notice, and I've gotten, actually, it's more recent years that the students have commented. It used to be students didn't even notice this, where they will say, well, isn't the saturated unit weight of the soil less than the unsaturated weight, less than the saturated? Well, the answer to that question is yes. For many academic problems, though, it doesn't work that way. That we usually don't worry about that for traditional academic problems. Sometimes I will make that adjustment, but if you don't see it, don't worry about it. Okay, with that out of the way, we have total unit weight 110 PCF, and the water table is 10 feet below the ground. Assume that the total weight is equal to the saturated. In other words, they're kind of, evidently somebody brought that up to them too. The feds beat that out of the way. And they said, so let's just assume that it's 110 all the way down. By the way, let me give you a little background on the Soils and Foundations manual. It dates back from the early 1980s when a federal highway employee named Richard Cheney, who I got to meet as a very, very good geotech, put this course together with Ronald Chassis, and he did that for a reason. Many of the people working in the state DOTs, which the Federal Highway Administration works with, were less than proficient in some of the basic concepts of soil mechanics and foundations. And so he put this together in order to familiarize them. It was designed for people of varying educational levels, and it was also designed to be practical. And they've expanded it since then. And to use it as a soil mechanics text requires a little extra work on my part to make sure that that we cover all the bases. And that's one of the reasons why we have Roy. But from the standpoint of a practical text on what soil geotech is really all about, it's hard to beat it, to give that. And so that's why I use it. I've always liked it, and I use it. For those of you, especially who are going into to work for the DOT, it will definitely serve you well to have it around. But in any event, let me go back to this. We see that we have the 110 PCF, and the water table is 10 feet below the ground. Plot a P-naught diagram and determine that P-naught 20 feet. If you do one, you'll get the other. So this shows you, this particular set of equations gives you the blow by blow on how to compute P-naught. If we start at 0, the total stress, since it's not saturated, it's above the water table, the total stress, the effective stress, and total stress are the same because the U is 0. So therefore, 10 feet times 110 PCF is equal to 1100 PSF, and that is the effective stress at 10 feet, which also happens to be the water table. At 20 feet, the total stress is equal to the total stress at 10 feet plus another 10 feet for that layer times 110 PCF. Now you say, well, why can't you do 20 times 110? You could in this case, but, and this is the important but, with effective stresses and with total stresses, let's just start with total stresses, it's very important to get into the discipline of always starting with the total stress at the top of the layer and then add what the layer adds to it. And then once you get to that, that becomes the initial stress for the next layer, and then that becomes the initial. So instead, you have to do it layer by layer. So get in the habit, because if you start seeing changes in the unit weight, you've got to do it that way. So with that, that's why we do it that way. So anything we're 2200 PSF of effective stresses, and then the U at 20 feet is equal to 62.4. I think I said 62.2 earlier. Forget about that. 62.4 times 10 feet, which is equal to 624 PSF. The effective stress at 20 feet is equal to the total stress at 20 feet minus the pore water pressure, which is exactly what this equation is all about. And you get an effective stress of 1,576 PSF at 20 feet. And that's the way you do it for all effective stresses. That's basically the technique that is used. Second example, an ideal IsoProfile. We're going to talk more in foundations about the relationship between most of what the problems you'll have in this course and the next one are idealized profiles. How you translate boring logs, which we talked about a couple lectures back, into idealized isoprofiles is one of the interesting parts of geotech. Requires judgment, all that good stuff. But we don't do it. So the ideal size profile looks like this. The depths, you see the first column right here are all your depth. And then the column next to it is the total unit weight. Now what they've done in this case is that they have created another column saying saturated unit weight and then buoyant weight. I'm not entirely sure. Well, actually, sure how they came up with, because if you subtract 62.4, you're going to get something different. I'm not exactly sure how they do that. Sometimes you have reason to believe that the effective, that the water is moving, in which case your effective may not be the same. Your pore water pressure, we assume for this part that it's all hydrostatic, which is Z time, it's the distance from the water table down to wherever you're at. See, for example, in this problem, the Z was at the surface of the water is at 10 feet, and therefore is 10 feet down to 20. But if you're given a problem like this, just run with it. Run with the saturated unit weights, buoyant weights as they are. This P-naught diagram should include a plot of both total and effective stresses and assume hydrostatic conditions. When you're confronted with a situation like this is how you do it. The solution is simply first of all, up to the water table, they're both the same. Fancy that. They should be. Your total effective stresses, unless you got capillary rise going on, should be the same in both cases. With that out of the way, then you have to have tabular results and calculations over here. Notice that they'd start diverging at that water table. Now you say, well, since they've cheated on us and they won't let us, didn't compute the submerged unit weights by subtracting the unit weight of the water from the total unit weight. How are we supposed to do this? Well, the way they did it, first of all, let's look at the total stresses. Now look at this right here is the column for the total stresses. It's no different than the total stresses before. And so we compute the total stresses in that way. Again, you see the way in which they start with, for the first layer, it goes down to 270. Then they have 270 plus what the next layer adds. Then they get to the third layer, and then 600 plus what the next layer adds. And get used to that. Get that into your discipline. Then the effective stress, they actually use the submerged unit weight method. This is a good illustration of the submerged unit weight method. Up to the water table, it's the same as the total stress, which it should be. After that, they just simply use submerged unit weights and compute what's below it. And then the hydrostatic pour water pressure, they do something really interesting, is that they actually, instead, I say that total stress minus pour water pressure equals effective stress. In their case, they rearrange the equation and say that U is equal to total stress minus effective stress is pour water pressure. And they come up with pour water, which would be different. You can check it for yourself than it would be if we just did the standard. One thing that you might want to go back and look at to see that this actually happens in reality is that the cone penetrometer test, for example, monitors pour water pressure as it's being pushed in the ground. And normally speaking, a cone plot will include the pour water pressure. And it will also include usually a little broken line for the reference pour water pressure. Well, the reference pour water pressure is Z times gamma water from the top of the water table. And you'll see those, they diverge. And there are various reasons why they do that. But for, again, our calculations, we're going to stick with doing it Z times that for most of the problems that you get from me, because that's the way we want to start. That also includes the last thing we want to talk about in this particular section is what do we do if it's below a lake or the ocean? How does that work? Well, I put this up. I haven't gone through all the calculations. I would strongly suggest that once you use this as an example, because you've got all the answers and you've got everything below, you've got all the answers, but I put this up to use this as an example to sharpen whatever, to see if you can get these calculations to come out. Because if you kind of reverse engineer this thing, that's fine. That makes it a lot easier. That's how you learn. But how do we deal with it? Well, we start at the surface of the water. And we say that the total stress is equal to the weight of soil, water, the combination thereof, times the depth. And that's exactly what you've got here. This first over here, the total stress is equal to the unit weight of the water, which is 9.8 kilonewton per cubic meter in the SI system, times the depth, which in this case is 3 meters. You get 29.4. Well, guess what? That's also the pour water pressure, or the water pressure, which I said the water pressure, for our purposes, is going to be the same whether we have whether it's in the pores or free water like we've got up here at the top. 29 point, and it's going to be 29.4, and 29.4 minus 29.4 is 0, which is basically a way of saying that the effect of the water of free water like this in a lake or an ocean or a river, assuming that hydrostatic conditions is going to cancel itself out. And that's how we deal with problems like this. So that's how we come up with it, and then the rest of it below that just proceeds as it would before. And you basically, the only difference really here is that instead of the water table being below the surface of the soil, it's above it. But we treat everything else the same way. The last topic in this lecture is capillary rise. Up to now, we've pretty much looked at the, above the water table and below the water table, and things are a certain way above and things are a certain way below. The whole topic of partially saturated soils and what's called the Vadose zone, is not a simple one, and we're not going to get very deep into it, but there's one phenomenon we really need to make you aware of is capillary rise. Capillary rise is a complicated subject. It is the result of surface tension in the water between a solid and the water itself. And basically what happens is that capillary rise takes place when we have when in a very narrow tube of some kind, and we're going to talk about that assumption in a minute, the surface tension of the water basically pulls the water up. And this is referred to as capillary rise. And it's kind of one of those, gravity-defeating, death-defying kind of things that under certain conditions can get you into trouble. It will, of course, like anything else in static equilibrium, the surface tension of the water tends to pull the column up. And when it reaches the point where the surface tension's force is equal to the weight of the water it's supporting, then capillary rise stops. A more complex phenomenon in soils due to the complex geometry of the particles. It's more pronounced in fine-grained soils because, as you see back here, we're basically, most capillary rise assumes a straight tube, and we're going to use the straight tube approach. And obviously, as your particles get smaller, your voids get smaller. Now, I say, well, that doesn't mean necessarily the void ratio goes down. What that means is that the voids are smaller. It's just that with smaller particles, there's more of them in a space. So, but generally speaking, as particles get smaller, the voids get smaller, and you get more capillary rise because those voids act like a tube to pull the water up. The straight tube assumption looks like this. And it's an equilibrium of the capillary rise force, which is on the left-hand side of that equation, and the water head in the tube, or the weight of the water that's pulled up, which is the right-hand side of the equation. And when those two forces are in equilibrium, the capillary rise stops. And generally speaking, for example like this, the larger, you can see this, the larger the tube, the less capillary rise you have, to the point where capillary rise in a very large tube, like it's on the left here, is negligible. So how do we solve this problem? How do we use it? Well, we do what we always like to do. We make a lot of simplifying assumptions. The surface tension of the water is assumed to be 0.0075 grams per millimeter. The alpha, which is the angle on the, it's a meniscus, and the alpha is that, we assume that equal to 0. The tricky part is the diameter of the quote-unquote tube, which we assume to be the D10 divided by 5. And we talked about the D values back when we talked about gradation charts and soil classification. And last but not least, the gamma water is equal to 0.001 grams per cubic millimeter. To keep things, because we do a lot of substituting and solving, and we end up with basically the z sub c, the height of that capillary rise. In other words, the distance here from the water table surface is equal to 150 over the D10, the ZC being in millimeters. Sometimes you'll see this formula in terms of 0.15 over D10. That means it's in meters. But in this case, it's in millimeters. Let's consider an example. Cohesive soil, the D10 is equal to 0.074 millimeters, number 200 sieve opening. Let's find the capillary rise in the soil. Z sub C is equal to, it's easy, you just plug and chug in the formula. Z sub C is equal to 150 over 0.074, which comes out to about 2,027 millimeters or 2 meters. And you see what the deal is here. The water table originally started here. And we're going to come back to that in a minute. And basically goes down 8 meters. We want to find out this. But the water table, basically what happens is that the soils actually are saturated above the water table by capillary rise. Because if you don't have saturated soils, you don't have, the tubes aren't full of water, and they're not really, so they are saturated. That's one reason why I define the water table as like I do. I say that the water table is the point at which the pore water pressure is 0. Because above that, if you have capillary rise, the pore water pressures, as you see here, are negative. And so the pore water pressure is 0. The soils are consistently saturated below it and sometimes saturated above it. Notice that the phreatic, again, I just said that, the phreatic surface was where the pore water pressure is 0. Since there is no surcharge, the total stress is 0. Thus, the pore water pressure above the phreatic surface is negative with capillary rise. And there's a positive effective stress at the surface to balance the negative pore water pressure. And we're going to see this in calculations. Let's take this case. Let's assume that the saturated unit weight is 20 kilonewtons per cubic meter. At the surface, the pore water pressure is negative. In other words, it starts at 0 and goes down up to the surface where it meets with the little meniscus, so to speak. By the way, one thing I point out is that capillary rise does not have to go to the surface. A lot of times capillary rise will go to the point where it stops before the surface. So keep that in mind as well. The total stress is 0 up there because there's nothing bearing on it. So therefore the effective stress is equal to 0 minus 19.6. The effective stress is actually positive at the surface. How about that? At 2 meters below the surface, which is the water table, the pore water pressure is 0 by definition. The total stress, it's still 20 kilonewtons times 2 is 40, and the effective stress is 40 kPa in normal. At 10 meters below the surface, or 8 meters below the water table, the pore water pressure increases to 78.4. The total stress is 200 kPa, and the effective stress is 121.6 kPa. And that's it. Without capillary rise, if we were to take capillary rise out of the thing, in other words, if we didn't have it, this is what would happen. At surface, everything is 0. Pore water pressure, effective stress is 0. At 2 meters below surface, pore water pressure is still 0. The total stress is equal to 32 kPa, 16 times 2, because what we've assumed, and this is where I made a concession to you, my students. You said, shouldn't the unit weight of the soil be less without it being unsaturated? Here it is. The saturated, it's 16 below, above the surface, as I said, and 20 below. So it's only 32 kPa, and the effective stress is equal to 32 minus 0, or 32 kPa. At 10 meters below the surface, the pore water pressure is, 8 times 9.8. The total stress is equal to 32, which is what the top of the layer says, plus 20 times 8. And then the effective stress is 113.6 is the difference between the two. It's actually the only reason why it decreased wasn't due to the capillary rise. In fact, if the unit weights hold, the capillary rise has no effect on the effective stress. The only reason why it changed is because the drying out, so to speak, of the top layer decreased the unit weight. If we had just said it's 20 and keep it simple, then it would have been the same. It has no effect. It only has effect below the, only has effect if that unit weight, if the unit weight doesn't change, which is kind of weird, then it doesn't have any effect on the effective stresses below. Now, let me make one important point to you, particularly for those of you who like to try to dig the internet and find solutions to my problems. There's more than one way to do this. There are some methods of estimating capillary rise, the effect of capillary rise effects on effective stress, which employ the use of the degree of saturation above the surface and that kind of thing. This is what Verroit presents, is the simplest way. It is not the only way, and it is not the only accepted way. And of course, there's also been challenges to the whole concept of the tube equivalence we just went through, which is an illustration of something I want to make very clear in geotechnical engineering. And that is that the tube, that there's very frequently more than one accepted way to solve a problem. And the deeper we get into this, get the foundations, the more obvious that will become. For the purposes of my courses, and there's a variety of reasons why I do it this way, I expect you to do it the way that I taught it. I loosen that up on design projects, but for the coursework, I expect you to do it the way I taught. And I'm not trying to be pedantic about it, but I expect that. I also will warn you in saying that you may get out and whoever you work for, particularly going to geotech, will look at the methodology I've taught you and say, well, this guy's a complete idiot. We don't do it this way. We do it this way. If that's the case, then you better learn. That's called lifelong learning. And they may be right for their situation. They may not, there's more than one way. The methods I teach in this course are accepted methods, but they're not necessarily the only methods, and they're not necessarily universally applicable in all different types of soils. Up to now, there's not been much difference. The capillary rise, I think, is the first issue the first place where this is really an issue. But I just wanted to make you aware of that. I expect people to solve problems the methods that I give them, and I also expect that you'll get out there and find out that there are other ways of doing things. So that concludes our lecture on effective stress and capillary rise. Until next time, thanks for watching, and God bless.